Good morning, everyone, and welcome to Fiber Broadband Association's Fiber for Breakfast. I'm Lisa Youngers, CEO and President of the Fiber Broadband Association. This week, monitoring our infrastructure, protecting networks, smart city integrity. Fiber optics can do all that. We're going to have an overview of fiber optic sensing. Before I introduce our esteemed panel, let me turn this over to Doug Weinbaum to walk through some housekeeping items for today. Doug?
Thank you, Lisa, and good morning to those who have joined us. I'm going to quickly go over a few logistical items. Please keep in mind all participants are in listen mode only. To ask a question, please type it into the question box located within your control panel. We'll host a Q&A session towards the end. This presentation is being recorded and will be available to members on FBA's website within 24 hours. You can find the recording in the Events tab under the Fiber for Breakfast drop-down option. And at the conclusion of the presentation, you'll be prompted to complete a brief feedback survey. We appreciate your input. I'll now pass it back to Lisa to introduce our panelists and get us started.
Great, thanks, Doug. So today we have joining us Michael Hines, Market Manager for Industrial Sensing at OFS, and Stan Fenley, who will be coming on here, Director of Legislative and Regulatory Policy at Corning. Fiber optics. Fiber optics do great things. We know we need fiber everywhere. It delivers the broadband at the speed that we all are looking for and with the capabilities we all need. But there's some other great capabilities of fiber, and that's fiber optic sensing. And Mike's going to walk us through that today. Mike, can you tell us more about FOSA first of all, and then of course, all the great things fiber optic sensing is doing and all of the great capabilities. And welcome, Mike. Thanks for walking us through this.
Sure. Thank you, Lisa, and good morning, everyone in the audience. Lisa, thank you for the invitation to the Fiber Optic Sensing Association to give you a briefing on distributed fiber optic sensing today. So this first slide is really just some background on what FOSA is. The Fiber Optic Sensing Association is really a spin-off of the FBA. We began in 2017 in Washington, D.C., and our primary mission is to provide education on the various forms of distributed fiber optic sensing, or DFOS, for various industries. And we do that primarily through webinars, videos, white papers, and most recently we're beginning to engage in documentation around best practices with respect to how you install and utilize distributed fiber optic sensing. Very active in the public policy space, so Stan Fenley will give us a briefing on that later in the presentation. That's a very, very big part of what FOSA does, particularly with new technologies. We introduce it to Congress and help in the sort of drafting of legislation and then interface with the regulators as well. Membership in FOSA is open to organizations globally who are involved in designing, producing, and marketing fiber optic sensing technologies. So over to the right of the slide, you have a list of the FOSA members, and these are all companies you may want to start paying attention to. They're all very active in the space, and they've got some really interesting technologies to chase. So let's see, Doug, do you want to transfer the control over to me so I can advance the slides? There we go. So today's presentation is about distributed fiber optic sensing, or DFOS. We'll explain what it is, how it works, and what you can actually detect with it. And then we've got a few kind of real-world examples of how it's utilized in various markets, and then we'll get the takeaways at the end of it. So let me just jump right into what fiber optic sensing is. If the slide will advance. Seems to be a bit of a lag.
Is there arrows in the bottom left once you click into the presentation?
Aha, there we are. Okay. All right, so let me just get myself realigned here. Okay. So the markets that we serve are depicted in this next slide. You'll see that it's not just one market like FTTH. We deal with pipelines, we deal with oil wells, we deal with third-party intrusion, perimeter security, borders, geotechnics, railroads, structural health monitoring, quite a few different markets. So the technology is sort of a general technology, and then it's applied specifically to the needs of these various different spaces. So we won't go over all of them. We'll just hit a few high points as we continue the presentation. So what is distributed fiber optic sensing? You'll notice, number one, that the word distributed is underlined, and that's an important concept to understand. With optical fibers in cable format, we can detect temperature, we can detect vibration or acoustics, and we can detect strain. And with these measurands, we can really solve some problems. Using distributed fiber optic sensing, assets like railroads in this picture can be monitored in real time, 24/7, and unlike point sensing technologies like thermometers or strain sensors, the actual optical fiber is the sensor, and you're using the time of flight of laser energy along that optical fiber to determine location. And because of that, you can turn the entire length of the fiber into a very long array of sensors with spatial resolution down as low as about 10 feet for practical purposes. So picture a span that's maybe 60 miles long. That's typically it's a previously installed fiber optic cable used for telecom. We just pull one of the fibers out, connect it to a piece of equipment called an interrogator, and then you simply have a system that works in the background, and you can monitor the things above: temperature, vibration, and/or strain. It's upgradable technology. People in the FTTH world will appreciate things like the use of conduits or bundled microducts as a means to install and then replace as technologies come to the market in the future. It simplifies everything, and this is a very good technology to use in those cases. There are some isolated cases where you need to actually directly attach the cable to the asset being monitored, but for all intents and purposes here, assume that you can basically bury the cables in the ground. So getting down to the physics, we won't dwell on this, but as I mentioned, we can detect temperature, strain, and vibration. The mechanism for detecting temperature in fairly short spans using multi-mode fiber is called Raman backscatter, and essentially the light is interacting with the glass itself. If you can appreciate, in a transmission system, you're injecting pulses of laser energy into the fiber, and your expectation is that it's going to go all the way to the end of the fiber and be detected. In the case of telecom, attenuation is your main concern, and attenuation is a function of backscatter. If we look at distributed fiber optic sensing, that backscatter is actually what we're using to determine what the environmental effects on the fiber are. So we actually tap into the backscatter piece, and we make use of that. So short distance up to about 15 or 20 kilometers, we use multimode and we use Raman backscatter. In longer length applications, we'll use Brillwind backscatter. It's a different mechanism, but with that we can detect both temperature and strain. And the range on that is out to something like 60 miles. And then finally, with distributed acoustic sensing, or DAS, we're detecting vibration, and that's really a different form of Rayleigh backscatter, which is what OTDRs use. In this case, it's coherent Rayleigh backscatter, and we can detect very, very small vibrations along the length of the fiber for its entire length. So how does it work? You'll see a bit of a cartoon on the bottom right-hand side. Basically, the interrogator injects laser pulses into the fiber. The naturally occurring scatter has a portion that is called backscatter. It gets scattered directly back at the source. We peel that out, and basically the environment is going to act on that backscatter, and we can delineate the differences and the effects of the environment on the fiber back at the interrogator space. The interrogator itself will allow you to scan thousands of times per second. It can pinpoint where events are occurring in near real time, 24/7. The interrogator is then connected to basically a processing unit that has the intelligence built into it. So algorithms that can basically learn from the background noise and then identify events. Some of the algorithms are preloaded. So if you're a railroad, you have a set of algorithms that you're going to use. If you're a pipeline, you have a different set. And these ultimately turn into things like alerts, alarms, and event identifications for the operator of whatever asset you're working on. So where does DFOS add value? in the following spaces: rail, pipelines, and smart cities. We'll spend a fair amount of time on rail because we have a lot of good examples there, and it's one of the operations that can take great advantage of the distributed fiber optic sensing technology. So if you're a rail operator, one question you need to think about is, if you had a single class of technology capable of tracking trains, detecting defects in rolling stock, detecting defects in the track itself, threats or trespassing issues, rock falls, landslides, fire detection in tunnels and stations, geohazard changes, catenary flashover. These are all things that concern the rail operators. If they had one technology that they could tap into very easily, like distributed fiber optic sensing, how could their rail operations improve? So this is the question that we're really exploring in the rail space right now. So here's just a quick video to kind of demonstrate the concept. And what you see here is just a video of a train in Austria. And as it moves along the track, it's generating lots of vibrational signals. And basically the fiber optic cable is buried alongside the track there, and it's picking up on the signals. So as the video clip ends in just a few seconds here, we'll get into some of the more detailed aspects of what the fiber optic sensor is actually picking up. So in terms of tracking trains, if you're operating a railroad, you want to know what the position of the train is. You want to be aware if a train stops, and you need to be able to continue to track it if it stops and it's not making any noises. So there's logic built into the processors that can do that. You want to know how long the train is, the direction of its travel, the speed of its travel, estimated time of arrival at either an incident or a station. And then you want to be able to interface with the control systems and SCADA systems that are installed alongside the tracks already. And distributed fiber optic sensing allows you to do all those things. A big issue for rail also is security and threat detection along the rail itself in the right of way. And this applies not just to rails, but to pipelines, perimeter security systems, borders and such. But you can detect foot traffic, human foot traffic. You can essentially detect if anybody's meddling with the fences trying to get into the protected zone of the rail itself. A big issue in the rail world is theft of heavy gauge copper conductors, which are typically buried in troughs along trackside. And if you have any tampering that's going on with those troughs or with the cables themselves, you're going to pick that up if you have a fiber optic cable running parallel to that with a defrost system connected to it. And then you can protect critical sites along the railroads to make sure there's no tampering or sabotage going on. In terms of asset condition monitoring, this is another part of rail operation. You can detect rail defects, track bed defects like subsidence using things like strain. You can detect errors in the overhead electrification, catenary systems. Rolling stock, a big issue with railroads, believe it or not, is that the wheels themselves generate flat spots on them. And as they rotate with all the weight of the train on them, they tend to work like a hammer and an anvil on the rail itself. So if you can detect flat spots when they're small, you can avoid damage to the track itself and then eliminate things like derailments. So the ability to track these events in real time and then pinpoint which train, which car, which wheel set, and which wheel have the issue really helps to sort of issue predictive or preventative maintenance aspects of rail operations. So it's a great way to keep your track in shape and avoid costly or catastrophic derailments. So just some examples of what we can detect with fiber optic sensing. We'll continue on. Here, we talk about safety. So we mentioned Raman DTS before and Brilwan DTS, distributed temperature sensing. You can use both of these technologies to monitor temperature within a rail station or often within rail tunnels. And if you have any kind of spike in temperature, you can pinpoint the location and investigate and mitigate it before it becomes an issue for the rail operation itself. Tunnel fires can be very catastrophic, and if you can minimize the occurrence of them or eliminate them completely through preventative monitoring, you've really scored big here. So safety and fire detection is a huge part of fiber optic sensing. Okay, safety geohazard monitoring. So if you have a railroad and you're concerned about the track conditions, one thing you need to kind of monitor is what's happening to the ground on which that railroad is built. So things like chemical weathering, freezing, thawing events, seismic activity, subsidence beneath the track. If you can monitor the ground that supports the rail, you can basically mitigate problems before they start to really affect the integrity of the rail itself. So geohazard monitoring is really the concept that does this. The next slide, we get into more catastrophic events. If you have a railroad that's got some very remote spaces and you have a landslide or a rock fall, until now it's been very difficult to identify the problem before a train comes along and actually interfaces with any debris on the track. So with distributed fiber optic sensing monitoring 24/7, if there's a rock fall event, you get a very large obvious signal, and you can alert the operator of the train so that they know to slow down or avoid that portion of the track well before they get to it. So it's got some really interesting safety features in terms of the use of distributed fiber optic sensing, and it's gaining a lot of acceptance there. And as noted down the bottom of the slide here, this applies to rail, but it also applies to things like highways and pipelines, etc. So the technology is general. It gets specific when it's applied in these different industries. Here we talk about pipelines. That's a big area of activity for FOSA. With pipeline operations, we're really looking for pinhole events where gases are escaping the pipe. They create a high frequency signal that can be picked up by the optical fibers. Negative pressure pulses. If an incident happens to the pipe, it's going to cause a wave of pressure from the point of incident back along the pipe. You can track that with fiber optic sensing. If a valve in a pipeline is turned inadvertently or incorrectly, it also creates a negative pressure pulse, and you can detect that and pinpoint where the issue is happening. Traditionally, in a pipeline, you would really be relegated to measuring what gets put into the pipe versus what comes out the other end to determine whether you have a leak. So let's say you've got a 50-mile length of pipe. You determine that you have a leak after about 1% of the flow escapes, and then you know you have 50 miles to really walk or drive to try to find that leak. With fiber optic sensing, you immediately know if there's a leak of any sort. You can catch it and pinpoint it within 10 meters instantaneously. So distributed fiber optic sensing can really solve some problems to make pipeline use even more safe than it is today. Other issues in the pipeline space are things like ground heave. We mentioned geohazard monitoring. These all affect the geometry of the pipe itself, and we have to make sure that the pipe physical position stays within spec, and there's no sort of excessive strain on the pipe that would cause a leak. Liquid impingement really talks about oil or water leaking from pipes. Again, there's an acoustic signal that's created with a small leak of liquid, and we can pinpoint that again instantaneously within about 10 meters pretty practically. So I think for the fiber to the home crowd, you're more tied into bringing advanced bandwidth to cities. Well, with all the fiber that's being installed in cities today, we can actually lay over the top of that and take advantage of it to do things like strain, acoustics, or temperature sensing. And the data is very rich, and it can be used by municipalities, by fire safety or police safety forces to monitor what's happening in urban environments. And I think over time, this will become a very important space, and you'll probably find that a small portion of the telecom market starts to really gain interest in how to use distributed fiber optic sensing in all its forms to add value for their own systems. So know that the fiber optic sensing technology is sort of creeping into the telecom space, and we think smart cities is probably where it finds a home soonest. But there's a lot of activity on behalf of the major telecom companies to start to investigate this technology. So that's coming to a city near you soon. Okay, we'll turn it over to Stan Fenley to give us a little briefing on public policy. Stan?
Thank you, Mike, and thank you, Lisa. Good morning, everybody. I'm Stan Fenley. I'm in Corning's Government Affairs Shop in Washington, D.C., and I am the chairman of FOSA's Public Policy Committee. First of all, thanks to Lisa and to the FBA for supporting FOSA. It's very important. This is an amazing technology and offers the opportunity, as Mike was talking about, for us to use fiber optics in new areas beyond telecom. So it's amazing. Just quickly, here are some of the issue areas that FOSA is working on in Washington, D.C. Hold on one second, please. Turn my phone off. As you can see, a lot of different areas, broad applications, therefore broad public policy issues. One thing you'll see it's in common with the FBA's policies is broadband. FOSA does support FOSA and its broadband efforts. In addition to that, there are all kinds of issues, as Mike mentioned, relating to pipelines, or mentioned relating to rail, smart cities. Dig once policy is one relating to highway infrastructure. You can also use I mentioned broadband. You can also use the technology for water resources, dams, water pipes, etc. The electric grid, border security. The United States government is deploying distributed fiber optic sensing on the southern U.S. border. We think that will continue regardless of the November election, regardless of what happens with actual wall construction. DHS has become a believer in fiber optic sensing. We think that deployment will continue. And then perimeter security. As you can imagine, this is a great technology for protecting large assets. And so all of those lead to a lot of work on a lot of different public policy areas in Washington, and sometimes at the state level as well. We're very active. I won't dig into the weeds on any of those today, but just be aware that we're working in all those areas. And if you have an interest in any one in particular, we would value your input. So Lisa and Mike, I'll leave it there for now.
Thanks, Stan. I'll take that. So thank you very much. This is, we wanted to highlight optic sensing as part of the Fiber for Breakfast series because it's such an important narrative for fiber overall. And frankly, I think one of the largest points is as we drive fiber further into communities, including rural communities, there are applications for fiber optic sensing, not just cities, but rural as well. So, and I think you all highlighted a lot of those. So getting to some questions getting in, what is the max distance from the track that makes the fiber the most effective?
That's a really good question. So the closer you are to the noise source, the better signal you're going to get. For practical purposes, the track right of way is typically something like 12 to 20 meters, and you can install the cable in conduit out actually fairly far to the outside of the right of way and still have an effective signal. There are new technologies being developed as well. So the interrogators are constantly being upgraded. The fiber optic cables and the glass fibers within them are constantly being upgraded. So we're finding that advances are being made to enable further what we call standoff from the actual event source itself. So lots of good stuff happening there.
Okay, great. And Stan, of course, jump in if where you would like. Second question that came in. This person asks or comments that a major issue in the past with distributed fiber sensing has been false positives. Can you comment on that? And has that been mitigated, or what extent is AI modifying or fine tuning maybe algorithms to improve that reliability?
Yeah, that's another really good question. I'd say that the false positive situation is sort of radically improving, and that's being done through machine learning and improved algorithms, AI. So if you picture the system, you install it, for example, along a railroad or a pipeline. You have a baseline that you start with, and you've got algorithms built into it to detect known signals. But those same systems are going to learn as they sit there and operate. So they get smarter with time. And that's how we'll ultimately get to sort of the mitigation of false positives.
Okay. And this maybe is for both of you. We have a question coming in about dig once. I know FOSA has been working in that area. Many states have developed dig once policies. Do you think policymakers are open to a string once policy? In other words, if electric companies are upgrading power lines and they're already on the poles, installing, repairing, replacing, would it be efficient to string fiber in the telecom space at the same time? Is the industry ready for that? So I guess comment on dig once and comment on, is there a possibility of a string once? You've been big on dig.
Well, that's really interesting and far sci-fi. I'm glad you asked. So first on dig once, there are a number of states that have adopted their own dig once policies. FOSA just did a review of state policies on dig once. We found that about 17 states have very clear policies. Frankly, some are better than others. If you want to know more about that, that paper is on the FOSA website, and we can point you guys to it. The issue of string once is really interesting because it's kind of an area where FOSA's public policy interest and Fiber Broadband Association's public policy interest overlap. You know, FBA has done a lot of work on trying to get municipal governments to reduce the amount of burden that they put on carriers in deploying fiber in the rights of way. It's been very influential with the FCC, as a matter of fact, and was just cited in a Ninth Circuit court decision. So very interested there. We have not gone to a formally string once issue, but we've talked about in the telecom world, I think it's one touch make ready kind of policies. So we're working on that, and that's been done more through the FBA than through FOSA. But it's very important in both settings. So thank you for asking the question.
Great. Mike, anything there?
Yeah, it's sort of complementing the public policy side. There are some good technical reasons to bring fiber optics along power conductors as well. So if you have a power line, less so in the distribution, more in the transmission line, whether it's buried or aerial, it's good practice to monitor those cables for temperature and also for strain. So what the power companies can do, if they've got a situation where there's maybe ice buildup on a cable causing the cable to sag, they can monitor with temperature and strain and determine where to inject more current and perhaps melt the ice off. Likewise, if there are heavy wind loads or if it's a very hot location, they can reduce the power load to cool the cable down simply by knowing where the potential threat for the power conductor is.
Okay. I'm going to take breakfast a couple minutes here and stay with a couple more questions. We have some use case questions coming in too. I'll hit you with them both at once. People are asking for, can you comment on fiber optic and its use in earthquake detection or seismic activity? And what about traffic monitoring applications? Mike?
Right, good questions. Actually, the seismic monitoring one is very exciting. So there's a lot of research being done now, and there's sort of proof of concept in the literature where a couple of groups come to mind. In fact, they're both FOSA members. University of California, Berkeley, and I think perhaps working with OptiSense equipment, have done some work on the campus at Berkeley, and I believe they're doing offshore work now and expanding into rural areas where they're taking distributed sensing equipment and they're attaching it to existing fiber optic cables, and they're able to actively monitor any seismic activity that's going on. So what does that promise? Well, it's possible, it won't happen immediately, but it's possible that you could turn the entire telecom system into sort of an advanced seismic detector. And if you can provide advanced warning, advanced detection of potential seismic events and triangulate using fiber optic technologies, you may be able to warn people sooner and essentially get them to safe places before major earthquakes strike. So there's a lot of promise there, still a lot of research to be done. The other part of the question, Lisa, if you would repeat that.
Can you comment on fiber optic sensing's use for traffic monitoring?
Right, yeah, so we're seeing some early uses along highways and to some extent experimentation in cities to monitor traffic flow, traffic volume. And we think that this is just a sort of an inadvertent opportunity. If you have fiber optics in the ground already and you use it for sensing, you can begin to learn any specific highway you could tap into that has cable next to it, learn about the traffic patterns, and eventually turn that into sort of traffic management opportunity for the local municipality or police force or what have you.
Can I jump in on this point? This is something I think should be of interest to this audience. You know, every city in America wants to be a smart city. Lisa, you talk about smart cities all the time.
Yeah, and smart communities too, not just cities, right? Yeah.
Yeah, smart roads, smart city. Every community wants to be called a smart city. Nobody knows exactly what the term means, but the question about traffic monitoring, everybody knows it means traffic monitoring, traffic management, looking for potholes, those sorts of things. I think the telecom community, the fiber community is well placed to really take advantage of that by frankly finding new revenue streams with municipal governments to sell them that kind of information or barter it for permits, right, and lower fees. And I know that there are a number of pilot projects going on around the country in this space, and a number of carriers that are looking at that and how they can utilize that information to their benefit. So I think that's something all of us in the fiber space and the telecom space should be interested in. So it's a great question.
Great. And one more question, I think, from the audience. Do these technologies all work with telecom fiber? If so, will that continue to be so in the future, or is there a need for, is it specialty fiber? What is the underlying technology there?
Yeah, another good question. So the technologies that we've discussed are designed to work with standard telecom fibers. So that's the real advantage of the system. You can plug them into what exists today. There's generally no additional cost to install new cables if you have them to tap into. If you get a spare fiber, plug in and go. Having said that, there are advancements in technology for specialist applications. So you may have a situation where a pipeline operator, for example, wants a super sensitive system, or maybe they have a standoff issue where they want to take advantage of fiber optic sensing, but they can't get close to the pipe because they don't want to dig near a pipe. So there are technologies being worked on very actively to enhance the sensitivity. Those would be sort of specialist items. So you'll have both in the marketplace, but I think for the purposes of the Fiber Broadband Association, most of what you're going to see there is standard telecom products.
Great news, and sound. Go ahead.
And this is one important point. To the extent that there's a free strand of fiber out there, you can turn your telecom network into a sensing network. Right. And so that can be very valuable using existing resources.
Right, that's a good point, and great planning, right? Very efficient. So going to give you both the final word. This is obviously an incredibly important topic. I think fiber optic sensing is so important to the entire narrative of fiber. I think it's important, and we all work together on this all the time. So Stan, what do you hope are people's biggest takeaway today?
So it's the point I just made. I think that there are already incredible fiber resources on the ground. And we should look at ways to enhance those for our customers. And to me, sensing is a way to do that. As I said, you can turn an existing telecom network into not only a telecom network, but a sensing network as well. That just creates lots of exciting opportunities for us.
And cities and communities should be aware of that as well. So
absolutely.
Great point. And Mike, you get the final word. What do you hope people's big takeaways here are today?
Well, I mean, here's a list of takeaways from the presentation, but I think the key point, as Stan points out, is we have the fiber in the ground in most places already. Let's try to take advantage of that. Fiber optic sensing is a really exciting place to be. There are new developments virtually every day. And we see the technology, it's fairly mature technologically, but it's also in its infancy in terms of application. So expect a lot more from fiber optic sensing in the coming decades. Also, we encourage all the audience to check out the Fiber Optic Sensing Association as a resource for information. So if you go to fiberopticsensing.org, we have a lot of free information. It's all high quality information. And if you have questions, tap into that, or feel free to give Stan or me an email, and we'll connect you to the right information sources.
That's awesome. This is really important information. Gentlemen, thank you so much for your insights and being here today. I think these are takeaways and really, really important in the ongoing story of fiber. So staying with this theme, being excited about our topics, next week, please join us. We are going to talk about the digital divide, obviously on everybody's mind, especially during the pandemic, shining a big bright light on who has broadband and where they don't. We're excited to have a couple of experts on this topic. So week 23, COVID-19 and the digital divide. How do we move forward? Fiber for breakfast next week. Thank you to Mike and Stan. Wonderful presentations. This has been a great topic. And to everybody, please join us next week and be safe and be well. Thanks, everybody. Have a great day.
Thank you all.
Thank you, everyone. Thank you, Lisa.